Okay, so let's begin, please. '23. Okay. Which this one? Before, after? 23 here. Okay. This one? Yeah. Okay. Let's go a little bit back. So we were looking at this problem, right? Equilibrium again. So where things are all, the forces are all balanced. So we see there are three forces acting on it. This tension T, and this is the angle theta, right? That it is making with the y-axis. The theta is the angle it makes with the y-axis. That's where we have to be a bit careful. So if you write the equation in the x direction, it's zero now. Okay, and there's no acceleration. It's equilibrium. In the x direction, you get F external, that is negative, because let me take the x direction this way and the y direction up. So plus T cosine theta or sine theta. That's the sine theta. Okay, so that should not confuse you. Okay, because the angle here, which I call as theta, whatever it happens to be, it is the angle it makes with the y-axis. So that's why it is sine of theta in the x-axis. Yes, yes. So this is, let me stop there. So if you know, can you, I mean, the question is to find, this is an unknown and this is also unknown, two unknowns. So this equation has two unknowns. Can you solve for any one of them? No. So we go to the y direction. And we need this equation, of course. Also zero, there's no acceleration, static rest. For this now, the mg is minus mg, okay, because it is in the negative y direction. T will be plus T cosine theta. It's in the y direction, but because the angle it makes with the y direction is theta, the y component will be T cosine theta. This is one of the places where, you just make a mistake, because you just remember, okay, x direction is cosine, y direction is sine. That is, you have to be very careful. And what about this guy? It is in the x-axis, so it will not, no, zero. So here there is only one unknown, right? So I'll not solve it, but I'll tell you what we should do. You substitute everything else, you find T. And T, right? T. Then you bring that T here and put in there, we can find F external. F, because we need to find both. Okay, so I can skip the solution part here because we already done that. We can go through it and then, okay, there are so many slides, but it is just, in big letters and slide by slide. Okay, so let's go to Newton's second law. Now, so far, we said equilibrium, meaning acceleration is zero. Now let's see what happens if there is acceleration. That is where Newton comes in and he says, the acceleration is proportional to the force, the net force acting on an object. Okay, this is what he said. And he said it is inversely proportional to the mass. You can understand it very easily by considering two objects. One is small mass, other one is heavy, okay, big mass. Both of them, you apply the same force, say 10 Newton and 10 Newton here. Which one do you think will have a great acceleration, big change in the velocity? The small one. So that means it has more inertia, right? Okay, the mass is the inertia. That's why the acceleration is inversely proportional to the mass. Yeah, we keep the same force. Now we are one at a time, right? Because we cannot change both at the same time. We want to look at the effect of mass on the acceleration. So let's apply the same force on both and see what happened when I vary the mass. So you can see clearly the effect is inverse. Bigger mass mean less acceleration. So you push with the same force both these guys from 0 in a few seconds, it will become 10 meter per second velocity. Here in the same amount of time, it will change maybe only 1 meter per second. Okay, so that is the acceleration. Okay, how fast the velocity is changing is the acceleration. So it makes sense, right? But it took the genius of Newton to first put it in a mathematical form and make it scientific, right? And this is understood, right? More force means more acceleration. That is understood. But here, this is another thing. It's not only the force, net force, by the way, because there can be more than one force. We have to look at the net force. And you have to also remember it's a vector. Okay, it is not simple magnitude only. It has both direction and magnitude. So you should know how to get the net force, vector summation. Then, it is simply the constant, we make it 1. So this is the Newton's second law. So we move to acceleration 0 before. Now we see what happened if there is an acceleration. This is the Newton's second law. So you should understand what force does is to change the velocity. Okay, an object can have a velocity and can keep that velocity without needing any force. Force is needed only to change the velocity. If the velocity is 0, it will remain 0 as long as it wants, unless a force acts upon it, net non-zero net force. Similarly, an object can have a, say, 10 meter per second velocity forever. Okay, it doesn't need a force to sustain that velocity. It will just keep that velocity. Right. So key point here, if a net force is applied, this is the statement of Newton's second law in words. If a net force is applied to an object of mass m, it accelerates in the direction of the net force, in the same direction. Not only that, the magnitude of the acceleration is directly proportional to the magnitude of the net force and inversely proportional to the mass of the object. So this is Newton's second law in so many words. So we have a concept question. When an object moves with a constant acceleration, what does it mean? Let's look at each of these statements. If something has a constant acceleration, can I say the velocity always increase? No. Always is the one that is giving the problem. If he says, okay, his velocity increases, yeah, okay. But when he says always, that is not correct. Constant acceleration means it has a velocity, a constant, constant acceleration means its velocity is changing steadily. Its velocity is changing steadily. So a graph of velocity versus time is a straight line. The velocity changes steadily. So if it is moving in a certain direction, it will keep moving in the same direction, because if the direction changes, the acceleration is not constant. If the direction changes, the acceleration is not constant. Or let me put it this way, in a velocity time graph, it has to be a straight line, because what is acceleration? The slope of the velocity time graph is the acceleration. So now we can have constant acceleration like this also, another graph. This is also constant acceleration, right? Okay, let me give one more object. This is also, all these three are constant acceleration. As long as it is a straight line, it is a constant acceleration. But it's a special value here. What is the value of acceleration for the black line? 0. For this blue line, positive. For the red line, negative, but constant. Okay, if we only look at each one of them separately, each one of these three objects have constant acceleration. So to say that velocity always increases, constant acceleration mean velocity always increases? No, because blue line is increasing, but the red line is decreasing. Black line is zero, okay, zero acceleration. Okay, so constant is that the velocity is constant. Okay, so velocity doesn't have to always increase. It couldn't be increasing, decreasing, or constant. Also constant acceleration. Okay, velocity is constant, acceleration is also constant with the value of zero. What about this? Same. No, we have to be careful. Okay, what he means is it is this whole journey. Do we have the same acceleration? No, because from here to here, one acceleration and then another acceleration. For the whole journey, can I say it's a constant acceleration? No. So this is also wrong. Not that. Its velocity sometimes increases and sometimes decreases, meaning it is not a constant acceleration. You have some positive acceleration, then you have a negative acceleration. No, it's not a constant. For the whole journey I'm talking about. Okay, C. It means its mass doesn't change. Okay, mass is a constant, so that has nothing to do with the acceleration. A force is exerted on it. Yeah, if there is acceleration, mean there must be a force, net non-zero net force. That is true. Okay, so if there is an acceleration, there must be a non-zero net force. Yeah.
The zero acceleration has a force.
No.
So it's
No, but yeah. Zero acceleration mean it doesn't need to have a force, but he doesn't say always. So we can excuse him, right? Yeah. Good question. Yeah. Constant. Yes. Zero acceleration mean constant velocity. Yes. Correct. Here we had a good point. Now, can you say this is correct, right? Because of course, this example, you don't need a force. Constant velocity mean you don't need a force, or maybe there are forces, the net force may be zero, or maybe there are no force at all. But here he is careful. He didn't say the force is always exerted. There is no always is not there. You can say a force is exerted on it. It means it's a kind of, well, okay, we will accept that answer anyway. A force is exerted on it. Okay, right. I mean, I'm sorry. It's not zero acceleration, it's a constant acceleration. So it is correct. It doesn't say zero acceleration, but the zero value is one of the constant. Yeah. Okay. Yeah, you are making it now. All right. Yeah, but anyway, let's accept that answer. Okay. So constant acceleration here mean probably I should change the with a non-zero constant acceleration. Then the force is always exerted on it. Okay, E, it is always falling towards the earth? No, that is one example. Always make is wrong. When something falling towards the earth, it has a constant acceleration, but it is the only one? No. There can be other cases where it has constant acceleration. Yeah. Of which velocity? Okay. Constant acceleration mean velocity changes in a steady fashion. Meaning in a velocity time graph, it is a straight line. So this is exactly what you're asking and exactly the answer. You're asking what is the meaning of constant acceleration in terms of velocity, right? So in a velocity time graph, it has to be a straight line. This is constant acceleration. This is not constant acceleration. Velocity time graph, what happened? The velocity is increasing, right? Okay. So there is acceleration, but it is not a constant acceleration. Here, the acceleration is this slope of this. Here, the slope of this. So the acceleration itself is increasing. Like, you know, in an XT graph, the slope is the velocity. In a VT graph, the slope is the acceleration. So here you have one acceleration, you have another acceleration, you have another acceleration. But what about this? It is the same slope. Tangent line is the same. So it's a constant acceleration. Here it is a non-constant acceleration.
Is the velocity in the straight line
First of all, it is VT graph, okay, right. So here the velocity is not constant, velocity is increasing. Here also the velocity is increasing. What's the difference between them? Here the velocity is increasing steadily. So it has the same acceleration. Here the velocity is not increasing steadily, you know, not in a straight line. So the acceleration is changing. It's okay? All right, okay. Yeah.
Can we call it constant acceleration in the XT graph?
No, why are you mixing? XT graph is something else. Yeah, okay. Hey, okay. Let me, okay, take this one. Okay. Now you're asking, this is XT graph. Okay, right. Now, the slope is the velocity. Velocity is changing. We know velocity is changing. But by looking at, can you say for sure the velocity is changing steadily? We don't know. Okay, is it a x squared? I mean, if this is a x equal to constant time t squared graph, a parabola, if you know the equation, but it's too much for us. I mean, we don't want to go to the calculus and all, okay? So if it a t squared dependence, then the acceleration is constant. But if it's a t cube dependence, acceleration is not constant. So we need some differentiation calculus and all, okay? We don't want to go there. Okay, so this is the answer to the question. So we already discussed that. Right, we come to the net force. So we know we can express the net force this way or that way. And the Newton's second law is net force is equal to mass into acceleration. So we need the net force when you do the question, because we may have an object with in 2 dimensions, there are forces acting in both x and y direction. So this vector equation can be broken into 2 equations, one along the x-axis and one along the y-axis, like we did in the equilibrium questions, okay? So how to resolve, we need to know. How to add them as vectors, we need to know. So let's do some examples. Okay, example number 1. The 60-kilogram skier is coming down a hill that has an incline of 35 degrees. So there's a picture in the next slide. So let me keep reading. If the force of friction between the ski and the snow, so this is the friction force, how fast does the velocity change per second? Do you understand what he is asking? Yeah. Yeah, this is an incline and the skier is here. Huh? Coming down, mean. No, incline is a common word, right? There is nothing called decline. Incline means slope. Yeah, you know, the angle can be anything more than 0 degree. Okay. Incline is a general word. Incline means any ramp. You heard this word ramp? Yeah, it's the same thing. Ramp. Got it? Okay. So now my question was, do you understand what he is asking? Yeah, acceleration. What is acceleration? How fast the velocity changes with time, right? So he's asking acceleration in many words. How fast does the velocity change per second? So you can cut the whole thing and say what is find acceleration? So that is what he's saying. Okay, find the acceleration. So now we have the forces, and he's asking us to find the acceleration. What should I use? Newton's second law. Net force is equal to mass into acceleration. If you know the forces, if you know the mass of the skier, then we can find the acceleration. But it's a two-dimensional problem, okay? Because we are having forces in a plane in both the x and y direction. Yeah.
Equal MA, right?
Yes. Net force, okay? You just don't just say F is equal to ma. I mean, yeah, the F is, there can be more than one force acting on the object with the mass of m and having an acceleration a. So it's okay, you can say F equal to ma, but remember the F has to be sum of all the forces acting on that. So let's say net force is equal to mass into acceleration. So what is the first thing we have to do? Draw the free body diagram. This is an important step. Okay, you cannot ignore that. So the skier is here, and he is interacting with the slope, the incline, and the earth. So these are the only two interactions. From the contact, right? It's in contact with the incline. So there will be surface forces. The perpendicular contact force, let me call it N, that is the normal force, and parallel contact force or the surface force, that's a friction. Which direction will it be, this way or that way, up or down? Yeah, up, because he is going down, right? The motion is down, so it will oppose the motion. So that is fine. The two forces are from one object, the incline, parallel and perpendicular to the contact surface. The other one is the earth. You cannot escape earth if you have a mass. So we call it W, which is mg, and so on. So we got three forces. And what is the next step? To show the x and y direction. So we're going to choose my x direction like that and the y direction. You should choose your x direction along the motion. Yeah. I'm coming to that. Okay. You actually only have three forces. What is the fourth force? That is not a separate force. Okay. This is not there. Just, I mean, we have only three forces. You have to tell me what is this force. This force is coming from the earth. This force is coming from the incline. I'll tell you, I will just forget that, okay? I'll come there. I'll be there in a minute, okay? We have only three forces. mg, normal force, and friction force. Normal force and friction force is from the incline. mg is from the earth. Forces are interaction, okay? It must be from another material, okay? Interacting with the skier, right? Now, then I choose my x and y direction. Now, look at the n. N is entirely in the y-axis. Good, we are happy. Okay, then it's easy for me to apply the equation. F is entirely in the x-axis. We are happy again. But this guy, gravitational force, has component in both x and y. This is where we do something clever. We know we need to resolve this. Let me do it from the beginning. So I will take this force, which is the gravitational force, and I resolve this force along the x-axis. I will call it Wx, and along the y-axis, I'll call it Wy. Then I don't need this. I cannot, I am substituting that one force by two forces, with two forces. So you cannot have all three. Either you have to have only the one force, or you have to have the components of that force. Now it's clear? Okay. Yeah.
So why you remove the mg for the gravity force?
I replace that mg by two forces. Its component along the x. Huh? Wx. Yeah, yeah. Okay, so you got it now, right? Is actually one force is substituted by two forces. The effect of these two forces is the same as one force down. We are just resolving that forces in the X and Y direction. Why do you do that? Because now all our forces, now we have 4 forces now, but actually it is 3 forces. We resolve one of the forces into 2 directions. All of these 4 forces are either in the X-axis or in the Y-axis. That will make our job easy when you apply the Newton's second law. That's the only reason we do that. Okay. Now, one other question I would like to ask, why didn't I choose the X like this and the Y like that? Why did you choose like this? Yeah, it will make the Y-axis equation easy. If I keep it like that, this is nothing wrong with that. Okay, we can do that. But by doing this, what is the acceleration in the Y direction? 0. So in the equation in the Y direction will be simple. Because whenever you have a 0 in the equation, it will make the equation simpler, easier, right? So that is the reason. Okay, there is nothing, in principle, it is not wrong, you can do that, but you are making unnecessarily complicated because you will have acceleration in the this Y direction, also in this direction. Okay. What I'm saying now, okay, let me repeat that. It's important, okay? No, okay, fine. Now this is how I choose. Yeah, we choose the X and Y axis, right? Why did I do that? Okay, why don't you ask me, why don't I choose X like this and the Y like this? Oh, there's nothing wrong in that. Okay, you can, instead of, you need 2 directions, it's a 2-dimensional problem. So when you want to apply in the net force is equal to mass into acceleration, is you can apply in any direction you want. Okay, so why don't I choose X like this horizontally and the Y vertically? Nothing wrong in that. But my point is, we are making it unnecessarily complicated. It will make our job more difficult. We can do it. Okay, you can try it as an exercise. Okay, challenge yourself. Okay, you will get the same answer. But why? I mean, this is really not needed. Okay. So this is, so you understand why we do that now. So let's now applying the equation is simple. Net force in the X direction is equal to mass into acceleration in the X direction. So now, see, since we have resolved everything, you don't have to worry about the forces in the Y direction. You only look at the forces in the X direction. Simply Wx and minus F equal to mass multiplied by the acceleration. Let me call that acceleration A down there. Okay. So this is, let it be, Wx will be mg. I mean that there are some things here, right? Because the theta is with the y-axis. So W will be mg sine theta, not cosine theta, and so on. Okay, but anyway, that's something I want to focus on the concept here. Now let me apply in the y direction. Net force in the y direction will be N minus Wy. What is this equal to? Acceleration in the y direction. 0. Do you understand that why the acceleration in the y direction is 0? This is your y-axis, right? It has no motion in the y-axis. It is entirely y. Suppose it's y coordinate. Let me say y coordinate is a big object. Let's say the center of mass y coordinate is 10 centimeters. When the person, right, skier, when he come here, what is his y coordinate? Still 10 centimeters, because he is moving parallel to the x-axis. So the y coordinate of that person is not changing. So there is no motion in the y direction. Therefore, this is 0. Okay. So let's look at the solution. I can skip that, right? So what is important is the concept. Yeah. Yeah. Okay. The one that I said just now about the axis. Okay, I will repeat that. Solve, yeah, okay, that is not a problem. Solving that I can do, but you want me to repeat the concept, okay? That's more important. Okay, right. I'm going to repeat what I said. Okay, net force is equal to mass into acceleration. That is Newton's second law. But this being a two-dimensional problem, I can apply it along the x direction and in the y direction. Let me start with the x direction. So net force in the x direction is equal to mass into acceleration in the x direction. Okay. Force in the x direction is, could you please quiet, please? Okay. How many forces we are looking at? 4 of them, right? So N and WY are in the y-axis. You don't have to worry about it because it has no contribution in the x-axis. So WX is in the positive. Now I'm doing this side is plus WX, and F is in the negative x-axis. So minus F. So I completed the left side. Now I will go to the right side. M is M. Acceleration. Let me say that acceleration is A, which is along the x-axis. So positive A. So I got this equation. I can stop there depending on what I want to do. So let me click the mouse to get it out. Okay. Now this is, I can continue. Okay. Since you want to solve it also, mg sine theta. Do you understand why it is mg sine theta? You got it? No, I'm not there yet. I didn't say 0. That is for the next one. Now you are still thinking about that. I'm repeating the whole thing. This is not 0. It has an acceleration in the x-axis. I'll come there yet. I didn't come there yet. Is this okay? Is this mg sine theta okay? F is okay. M, A, fine. Now this is over. Okay? This is over. Suppose I know M, I know theta, yes, F is given, I can find the acceleration. Okay, so the calculation part is done now. You want to, someone asks you find acceleration, this is all given, this is given, this is given, so you can find acceleration. Okay, that's, in the calculator. Or you use the solve mode in the calculator. You don't need to do algebra. You put the x as the unknown, a is the unknown, then you can ask the calculator to solve it and get the answer. Now comes the other thing. We can also apply the Newton's second law in the y direction. Are you paying attention? I have to get your name. Sorry, what's your name? Muhammad. Okay, so this is over. Okay, now we know we can apply the Newton's second law in the y direction also. That's the independent equation. It's another equation. Now probably that is why you asked me to repeat it. You want to understand why did I put 0 for this? Okay. So first let me do the left-hand side. Okay. So it will be n minus wy, which will be mg cosine theta, equal to right-hand side. M is m. For the acceleration, I put 0. Now you're asking me why is it 0? In the x direction, it is not 0. In the y direction, it is 0. Now let me tell you why it is 0. This is your x-axis, this is your y-axis. When the skier is here, what is his y coordinate? Let me say let's say 1 meter. His y coordinate is 1 meter. Are you listening? Okay. When he is here, what is his y coordinate? Same level. In the sense parallel to the y-axis, right? Here his y coordinate is 1 meter. Here also his y coordinate is 1 meter. So did his y coordinate change as he is going down? No. So that means acceleration in the y direction is 0. You got it? Okay. All right. Why? Okay. Maybe there is no need. Suppose he asked me to find n. Then I need to solve it in the y direction. Okay, but that is not in the question. The question, he only asked you to find the acceleration. So we don't even have to do this. Why waste the time? Okay, but maybe we can change the question and ask to find the normal force. Then you need to apply the equation in the y direction. Okay. So these are the solution. Third law. Third law talk about two objects interacting and the forces between them. Let's say we have object A and object B. If they are interacting, there will be that the interaction is actually the force between them. So if an object A exerts a force on B, and let me call it F A on B. So A exert a force on B. Is that the end of the story? No. He will return it. B doesn't like. Okay, he not doesn't like. The interaction is always mutual. When A exert a force on B, B in return will exert a force on A. This is what happens. And not only that, we have, I mean, Newton said more than that. He said these two forces will be equal in magnitude, opposite in direction. This is the Newton's third law. Okay. So you loosely say action reaction. Okay, that is what it means. So it always come in pairs. Yeah. Anything, not only anything. You don't have to be touching. Okay. You know the gravitational force between moon and earth. When the earth is pulling the moon towards it, moon is pulling the earth towards the moon. Okay. Is always the forces are equal and opposite. Same magnitude, equal. In magnitude, opposite in direction. So force, and this is how you put it mathematically. Force on A by B is equal to force on B by A with a negative sign. So that negative tells you the direction is opposite. I will take attendance and I will continue. Yeah, I think I skipped a slide, go back. So we have a concept question to understand, to see how much you understood Newton's third law. An astronaut stranded in space far away from spaceship orbiting the moon because the removable jetpack fails during a spacewalk. So let's say this is the astronaut and this is a space station. He cannot go back because he uses the jetpack, because you put the gas in one direction, you'll use like a rocket, then you move forward. So you push the gas away and the gas will push the astronaut in the other direction. Okay, that is what happened when you use the jetpack. Yeah.
In the X or Y direction?
It's in the space. Okay, you can, yeah, let's say this is the astronaut. There is no up down, okay, in the space, because up down is because you have a gravitational pull. The direction of the gravitational pull is the down. Okay, so for you are in the northern hemisphere. It is one up down, and people in Australia, it will be in the other direction, is be down. Okay, so anyway, here is in the space, so we can say he wants to say right side. Space station is to the right of him, so he wants to go to the right. Can he walk in the space? No. How do they go back? Either they have a cable, something attached to the line, or they have this jetpack. So they will, like a jet plane, you can put the exhaust gas out. So you are pushing the gas, and the gas will push you in the opposite direction. Newton's third law. Now this jetpack is not working. He has the jetpack. It's not working. Can you use the jetpack to get back to the failed? Come on, think. Yeah. He wants to go in this direction. Okay, let's say this is your X direction. Yeah, he cannot walk. Okay, because there is nothing. Cannot swim. Okay, there's no air. Yeah, no water, no air. Yeah, push mean he has to throw it, right? Like he throws the gas out, exhaust jetpack. Now he has only one thing. he has to throw the jetpack. So when he pushed the jetpack will push his hand in the other direction. But you will say, oh, it's a very small force. Will it help? It will. You know why? Because there is no air resistance. Even if you get a very small velocity, acceleration is 0.1 or whatever, that's enough. As long as he managed to get some velocity in this correct direction, that velocity will not diminish. There is no air resistance, nothing. So he pushed the jetpack in this, he give a force to the jetpack with his hand, he pushed this, then in return, Newton's third law, jetpack will give a force on his hand in the opposite direction. That small force is enough to give him a small velocity. No matter how small it is, he will keep that velocity, and if provided it is in the correct direction, he will come to the spaceship. Okay, just a small velocity is enough. Okay, good, because there's no air resistance here. I mean, y, x, y is your name, right? This direction, you can call it x, you can call it y, you can call it z, you can call it a, you can call it b, whatever. Yeah, if he pushes down, he will go up. He will not go toward the spaceship. So you have to throw it the direction away from the spaceship. Okay.
So the force is equal exactly.
Oh, yes, exactly equal. If you push the jetpack with a force of 10 Newton, the force on your hand from the jetpack will be 10 Newton. But 10 Newton is not a big force, by the way. Okay, whatever force we can give. But it doesn't, suppose the astronaut weighs, say, 100 kilogram. Yeah.
There's no fraction. How the jetpack will push the human?
Newton's third law.
So I mean, there's nothing.
Newton's third law doesn't assume anything. If you push something with the 10 Newton, that thing will push you in the opposite direction with 10 Newton. There is nothing. That is Newton's third law. Yes?
Opposite your side, that will be friction, but there is no friction. That means you will not push anything.
No, you are confusing something else, okay? Now you're talking about walking on the earth and the friction, those things, right? That is, you're pushing the flow back, the flow will push you forward. But in the space, there is nothing except you. You are there, okay? There is no flow to push, no air to push back. Like in the water, you push the water back, water push you forward. Here, even if you consider the air to be the water analog, there is no air also in the space. So you cannot swim back toward the spaceship. The only way is you throw whatever you have. When you throw, you apply a force on the thing that you are throwing. That thing will give a force in return in the opposite direction. So only way out is to throw away from the spaceship. Whatever you want to throw, you throw away from the spaceship. So that thing will push you in the direction toward the spaceship. Okay, the force is small, I agree. But it doesn't matter because we are in the space. Let's say the force is only 10 Newton. Your mass is, say, 100 kilogram. Okay, so 10 F is equal to ma, 100 kilogram into A. A will be 10 divided by 100. Acceleration is only 0.1. Fine, doesn't matter. There you have an acceleration of 0.1 meter per second every second. Every second your velocity will increase by 0.1. So you start with the 0 velocity. After 1 second, your velocity will become 0.1. Okay. It's acceleration. The force is instant, right? It's only at that moment. So when you push while it is, lose contact with the object, it acts for a small period of time. In that period of time, you will get some velocity, say 0.1. After that, there is no force. So whatever velocity you got, the 0.1 meter per second, is enough because that velocity is not going to diminish. Why? There is no friction, there is no air resistance in the space. So that velocity is enough to, it might take longer time because it's only a small velocity, but eventually he will reach the spaceship. Yeah. Yes, constant, because force is not continuously acting, right? Force is acting for a small time. In that small time, your zero velocity will become, let's say it acts only for 1 second. You are in contact with the thing only for 1 second. During that 1 second, you will acquire small velocity, say 0.1 second, 0.1 meter per second. So fine, he will just move with 0.1 meter per second. So what? There is no air resistance. So the velocity will not decrease. He will go with a constant velocity and he will reach the spaceship. Okay, we are spending too much time. I need to go to the next slide, please. Okay, right? So this is the answer. Concept question. Newton's third law states that when two objects A and B interact, the force of each on the other has an interaction pair B on A that is equal in magnitude but opposite in direction. It's a kind of a trap question, okay?
This is the
Third law. This is third law. So when A and B interact, there will be two forces equal in magnitude and opposite in direction. So it's really, the question is wrong in the sense, okay, there is some flaw here, an error here. I want you to spot that. So we have two forces. What is the sum of the two forces? They are equal in magnitude, opposite in direction. If you add them, what do you get?
Zero.
Zero. Okay.
No.
Yeah, okay. If the net force is zero, we know from Newton's second law, acceleration has to be zero. So he is asking, does it mean we need some force that have no interaction partner for an object to accelerate? If an object to accelerate, we need non-zero net force. Yeah. Yeah, there's a trick in the question. Okay, I will repeat what I said. Now I'm asking you, Newton's third law says the two forces A on B, B on A, equal in magnitude, opposite in direction. If you add these two forces, what do you get? Zero. That is the question you asked me. What do you get? Not in? Why do we add it? Yeah. Yeah, you are giving the answer, but you're not putting it correctly. Yeah, you're almost there. You are getting it, but you're not telling it properly, I think. We apply this equation on one object, right? We apply this equation. The net force on object A is equal to mass of object A multiplied by acceleration of object A. The net force on object A is only the force, one force that is coming from object B. Why do we add the two forces? Because, okay, I think that's what you are trying to tell me. So the point here is the two forces are not acting on the same object. One force is on object A, the other force is on object B. Yes. Yeah, because if we have the force on A from B, and there is a force on B from A. So the FA and FB. FB is the interaction partner for FA. FB is the interaction for vice versa. Okay, right. So he is telling, I mean, if forces are always coming in pairs, their sum is zero. So how does anything get a non-zero acceleration? So the question is, it's a trick question. So your answer is, you got it wrong, because the forces are acting, the two forces are not acting on the same object, they are acting on two different objects. So when you apply the Newton's law, there is only one force. The other force is on the other object. So why should they add them? In this object A, there is only one force. So the net force will be that force, not FA plus FB, only FA. Okay, right. So no, the two forces are acting on two different objects. So the net force on each object is not zero anyway. Okay, that's a short answer. I was explaining a lot, but that puts everything together. The time. Okay. What is the time now? Bring my watch. Yeah, we have some time. Like, give me just it's okay. 5 minutes. Give me 5 minutes, please. Surface forces. We are revisiting, right? Surface forces are when two things are touching in contact. We have surface forces. The parallel surface force, that's the friction, and the perpendicular surface force is the normal force. And tension. We looked at tension before. Tension, in a cable or a rope, if you take any point there in the middle of the rope, we have, the tension in acting on that point in both directions. But when it tied to a certain object there, the tension will be on the object upward, on the ceiling it will be downward. So the tension everywhere is the same. Okay, it's a concept question. I know it is going to take time because you're going to ask me question. So we'll stop here, okay?
No more
No more. All right. But please look at this and think about this question, please.